Into it. Chapter 10. Finish this chapter up today. Kind of run a quick schedule for the week. So today we're going to finish chapter 10. Tomorrow we're going to have a short test review. So we'll do a test review over chapter 10, and we are going to test over that material on Wednesday morning. We're also going to start a new chapter tomorrow. We're going to move to the sectioning chapter, which is an orthographic type of deal. Yes, Becca?
The challenge course is tomorrow, though.
Is tomorrow the challenge course?
Yeah.
What time is that again?
From
9?
9 to
It was
12,
9.
yeah.
Okay, so we'll just do the test review in the morning.
Okay.
By the way, on the challenge course, those of you that don't participate in the challenge course, you're expected to be in here, okay? Where I'll be, and we'll do some fun items. The other people are out doing a little team building or whatever we do on the challenge course. Is everybody going, or how many people aren't going? Missy, you're not going? So it's you and me? Majed?
So there's two. Are you
Is there
going?
heights? Like, I don't do heights.
That's
That's
the
challenge.
point.
That's challenge.
You
Okay.
gotta
That's
trust
the whole
us.
point. Is stepping outside your box.
I don't do heights.
I don't.
We'll just-
I
We'll blindfold you and carry you across, okay?
I'll do it.
Yeah, everybody's afraid of heights. I mean, that's a natural fear reaction, right?
I'm not afraid of heights, I'm afraid of falling.
There you go. It's not the heights that bother you, it's the landing.
Exactly.
Seriously.
All right, let's jump into that. Now, really, we've only got a couple things left to take over. And I think you can kind of coordinate most of this chapter basically on understanding what we're trying to do as far as orthographic projection and the glass box. Realizing that when we analyze an object, we are at infinity. Therefore, as we look at it, everything that we're looking at, our rays of projection are parallel. They're perpendicular to the plane of projection. Therefore, the object appears true size and shape. Now, keep in mind that many of us, as we learn how to project, we start with points. So we understand, oh, I'm up in the top view of the horizontal plane of projection. That has a relationship to the frontal plane of projection, so I can project directly into it. That's the first law of orthographic projection. Once I determine these two, then I can use that information to locate that point in any other view. Now, if you can locate a point, folks, and you can understand that process, then it's just another logical step to the next one, which is projecting lines. Because we're looking at geometric breakdowns, right? And a point is the base geometric unit that we have. Now, once we get that, then it's not a huge step to projecting lines. Because what's a line? It's the shortest distance between 2 points. So now we take 2 points. Right? And so we take just a line. We can project that due to law 1 right into an adjacent view. Once we have those two, we can use the other laws to locate that in any other view. So we start with points. Does everybody understand points? How we project them? Then lines are the next step where you're doing 2 points. Gets their level of complexity, jumps by double, but it's still the same process, right? You're just doing it again. Then we go to planes, and planes can really have kind of an unlimited number of points, but there will be points or vertexes that define those planes. And again, we can take these planes, instead of looking at the whole plane, break it into points, because we already know how to project a point. Now we might have 3 of them, we might have 4 of them, we might have 6 of them, whatever the case might be, but we use the exact same process all through it. At the end of it, we end up with a 3-view drawing. So that's really kind of the learning curve, at least in my opinion. I know a lot of times people will start really at the third part here, where you're looking at planes and trying to project those. And I think probably many of you have been very confused on that process. As you look at these planes, oh, what is this plane? Is it normal? Is it inclined? How's it going to project? Well, don't forget, you can break that plane to lines You can break that line to points. And by doing that, then following the 8 rules of orthographic projection, you'll get a successful result when you do these. Now, the author has a bunch of stuff at the end of the chapter that might be useful for you in the visualization and application of these skills. We've talked about some of these already, but let's review them. First one, let's go to figure 1070. So a visualization tool, clay. It's a pretty good process. I think some of you have really taken this on, and I would ask you out there, those of you using clay, is it useful to you?
Sometimes if I get it right.
If you get the clay model right. Okay. But if you do get it right, then it's extremely useful.
Oh, exactly, yeah.
Yeah. And it's a process, you know, kind of like the author states here. The way to do the clay is start with some cube that has the overall dimensions. Take the tip of the blade and sketch your views on the sides that you pick. And you're just taking the tip of the blade and just kind of outlining everything. They don't have to be exact with clay. You're looking for shapes and how they're going to appear. And then once you do that, you start looking for lines that match up. And you say, oh, well, that one's got to match here, so therefore those two are related. Now I've got the same vertex point between these two surfaces and whatnot. By the time you get to the end of it, you got the completed result. Keep in mind, when you take the test on Wednesday, I'll allow you to use the visualization tool of your choice, because I think it's part of 3-view drawing. If you're using clay, since we don't have enough for the entire room, and we don't want a mad scramble to go get your own, okay, for the test. Okay, so if you use it, that's all I'm saying on that, because we only got so much back in the drawers, right? Okay, so if you want to use that too as a visualization tool, get your own. So clay models are a great way to go. Another way, and this way that is really kind of, I think, probably the majority of the class is using this one from what I've seen. Sketch isometrics. It's really, in essence, the same thing as a clay model, but you're providing a 3-view or a 3-dimensional pictorial view so that it helps you visualize the tool. Some of you are sketching these. Some of you are doing them on the computer. That's fine with me on all of those ends. And yes, if you do sketch isometrically on the computer for your test, you can use it as a tool. Okay, so this will be one where I don't make you close the computer down, but you can only use it for the visualization part. Okay. How many people are using isometrics? Yeah, I thought at least half of you. You guys know we have a bunch of isometric grid back here in the paper, in the drawers? Yeah, there's a bunch back there. Now, we don't have enough to just go in there and start wasting it. What really works well on an isometric is grab a piece of vellum and set it over top of the isometric grid and then just sketch on it. That way you use the same isometric grid for several times, and those little packets they're fairly spendy as far as paper goes. So if you do that just to make it stretch a little further, that would be nice. I've actually even got a drawing that's an isometric grid that I print off that's a real thick, and I can see it through bond paper. And I just sketch on bond. That's cheaper yet. Not that we need to watch the pennies that closely, we're not my mother, but we do have to be economically viable. Isometrics, great visualization tool. Great visualization tool. If those two fall down for you, then the author gives you a couple other ones. We've already mentioned figure 1071. We mentioned this way back in drafting 131, and I think quite a few of you deal with this. I know a couple of you, when we sat around and talked about drawing, said, I look for shapes. Okay. Well, do your geometric breakdown. Break your object into shapes. It will break down into some facility of these type of objects, where you have cubes, rectangles, triangles, circles. You might have positive shapes, you might have negative shapes. But if you break them into these surfaces, then you can go back to some of these other pages we talked about, and you'll know how they're going to project. And by that, if you break into these guys, the other ones I'm talking about is page 535. Because if I know what a circle appears and I come right to page 535, I go and find, oh, there's a concentric circle cylinder, negative, positive. How's that going to project? Okay, in this case, this is a counterbore hole. So you can go ahead and look at those. There's another page that we also threw out on that didn't have all of the objects together. It had the individual shapes, and this was on page 522. Remember this page? Where we started looking at the different 3D primitives that we got back in 131 and then how they projected. So a couple good resources for you if you do the analysis by surface or the breakdown of objects. The author brings a couple other items in. If you look at 1075, these are kind of checks. They call this surface labeling. This is when you have a physical object or an isometric or a clay model, you finish your multi-view drawing, then go back and look at your individual surfaces. Just because you draw that last line, folks, on the computer, and you say, it looks good to me, print. It shouldn't go in that box. You should pull it out, sit at your desk, put a scale on the thing. Does it really scale 1 to 2? Does it really scale 1 to 1? Okay, check all that stuff. There's really nothing more embarrassing than in workforce, turning in a drawing to somebody and they said, well, aren't we doing this at 3/4? And you got the thing at 1.5. Yeah, well, that was part of the instructions. So check that stuff. Make sure you got it right. Do a double check. Remember the old highlighter thing. Highlight that. That's done. That's done. That's done. Run it by a peer. Those things are all done in the workforce. Now on this one, what they're doing is they're just saying, okay, I'm going to label this surface 1, and then we'll go and make sure on my other one, this is what I'm getting. On the top, I got a rectangle, I've got an edge here, I've got an edge there. Yeah, okay, that's a normal plane, that's what I should be seeing. So I'm kind of analyzing it after I'm done. Doing a check. So analysis by solids, or surface. And really, when things get very difficult, folks, in essence, this is the fallback. This guy right here will always get it right if you follow. What they call this is vertex labeling. When you get really tough surfaces, this is the one I fall back on. Now, when you do this, there's a convention here. So when you do this deal, notice they got 9, 8, 10, 7. Okay, there's 2 here because it's a line and you're looking at it as a point view right here. So whenever you do this, put the point that is closest to you first, the one that's away from you second. So if I'm looking at this top edge, you can see 9's right here. Well, it's closer to me than point 8, which is at the back. Okay. And that will keep those in order for you. Again, point labeling. And when I get oblique planes and I have to do 3 or 4 rotations to display these things, this is really the tool that will keep my mind from going nuts, because I'll be able to track those numbers as I go through in these different rotations. Another really good technique. That's the ones the author kind of gives you. Is there any others out there that you folks have just kind of found out on your own and say, this works for me? Or just draw it and hope for the best? Okay, well, those will give you a base. Again, these are just techniques the author's thrown out that a wide part of the population has success with. It doesn't mean it's the only way. Okay, like I've mentioned many, many times, all our minds are different. We've got to play with it. We've got to steal from one idea, steal from another idea, and blend them how our mind works. And use those to get a successful completion. And really, the only way to steal from these ideas is to try them. Give them a try. All right, we have three things at the end of this chapter that we do need to talk about. And these are some conventions to clarify the drawing. Remember, when we do a drawing, really, all drawings need to follow only 3 rules. And that's the 3 C's. And we've listed hundreds of guidelines, and you use these guidelines to get to the 3 C's. Does anybody remember what the 3 C's stand for?
Clear, concise.
Yep.
Clean.
Clear, concise, complete. Okay. These 3 conventions we're now going to talk about are in the clarity stage. So when we get projections that are extremely confusing, we're going to do some things that break the rules of orthographic projection, but they clean the drawing up. Okay. That's what these 3 items are. So the first one is a partial view. And let's go to page 543, figure 1083, and let's look at what a partial convention is. By the way, this is a convention. It is an accepted deviation from a standard, right? Which our standard is the glass box, orthographic projection. Since it is a widely accepted deviation, we do not have to tell somebody when we pull one of these out of our toolbox and start to use it. Okay? It's just assumed that the reader will know. If they don't know, that's their problem, not ours. So the first one's a partial. We use a partial view when the original projection adds no new information or leads to a confusing projection. So this is an example of doesn't add any new information. Here we have a front and a right side view. Okay. So this part right over here is symmetrical. Do we really need to show it? No, we don't. So you can break it one of 2 ways. You either break it on the center line and you leave half of it off. They know the information is right there for the whole thing. Or you take it slightly past it and you use a short break line to display that break. Remember, a short break line is a hand-drawn line to represent how the object breaks, and it's very thick, right? It's on the border layer. So you can use either of these. Works great for symmetrical objects. It doesn't have to be a circle either. It can be any symmetrical object. So this is a good one for circular things, or, as I said, symmetrical. There's another example on the next page at the top. This is on the partial views. This is really probably the one I use the most. So in essence, we're given a front view. Okay. So here's our object. It's got a couple arms coming up for some reason. It's either attached, and I'm guessing that maybe a shaft goes through here or something like that. Okay. So here's an object, our front view. As we take it, this is the true projection, where we see this one right here, and then right behind it here. Now, that's a pretty confusing view, because everything kind of lines up, and you start thinking, oh, this surface is here, this surface is here. No, it's not. It's completely on a different portion. And so what we end up doing is we end up just kind of breaking the object right here in the middle. Okay, so we're just going to break it, we're going to rotate it, and only display that portion. So they turn it, get it to here. That's real easy to read on that end. Fairly simple construction. Much easier to build than this one, or to identify what we're trying to build, I guess might be a better way to say it. Then we take it and we turn the left side view for this one. Again, now we're given 2 great looks at that one and that one. No mistakes are going to be made. Easy for them to read. They can decipher these 3 drawings maybe in 2-3 minutes, right? I think you folks are probably deciphering it right now, and you probably got an idea of what it looks like in your head right now. Imagine if you would have started with these 2. You'd probably be 10-15 minutes trying to figure that out.
So I don't understand.
No, they're not symmetrical.
You just said that partial view is used for symmetrical.
Or you don't add new redundant. If your view does, let me.
What's the difference in multi-view? Doing, the right, left, front, right, and left in the top
Okay.
view? I mean, that's, why would you call that partial?
Okay. Here's my true definition. Object not entirely shown due to confusing projections or redundant information. Maybe I should have read that.
Object not
The first example was redundant information. This one's a confusing projection. Okay. So let me state that again. Object not entirely shown due to confusing projections or redundant information.
So you'd use a partial view in the place of a multi-view.
Yes, you're still doing orthographic projection. But if we were looking at a left side view looking this way, this is the true projection the glass box gives you. So what we're just going to do is we're just going to chop it off. We're just going to say, boom, I'm just going to go here. I'm only going to rotate this over, give them that projection. Now this one requires 3 views. It requires maybe even a 4th because I got depth, but I might do the top also. But I'm getting this view, the front view. That gives the orientation of these arms in relationship to the base. Okay, they've got that information. Then they only need information on this guy and this guy. So we're going to rotate this one and that one as opposed to the true projection because they're confusing. Okay, do you get it now?
Yep.
Bottom line is you can pull this out of your toolbox in more than one place. By the way, I love drafting toolboxes. They're light, okay, but they do get pretty filled up and they get cluttered until we get really used to these things. Any questions on these? The partial convention. The object not entirely shown due to redundant or confusing projections. The next one is the revolved convention. And I'm going to put my definitions up here so I don't butcher them again on this Monday morning. Revolved convention. Object rotated to quadrant points to allow object to be displayed true size and shape. A revolved convention. Objects rotated to quadrant points to allow object to be displayed true size and shape. This is one you're almost always going to do when you have things about a center point, which there's a lot of things like this. You know, just so you know, and you can kind of think of it, why are there so many objects that are on a center point? You've drawn quite a few of them. Why are there so many objects that have a center hole and then things rotate outside of it? Why? Think of how we power stuff. The internal combustion engine, there's only one power source and you run a heck of a lot of things off it. There's one central shaft that thing turns. And it's powering a whole bunch of devices. Electric motors, same thing. They're all rotary, right? They all turn. Therefore, most of our power-driven devices come off of shafts. Okay, so that's why we get so much of this stuff. All right, let's go look at this in action. Figure 1085. Now the 1086 is the one that really points it out. So here I have some flywheel of some type. I'm guessing that a shaft comes in here. These things are attached to something and it's turning. Okay. Well, here's your true projection. Now keep in mind that every one of these spokes, this one, this one, this one, this one, this one, they're all identical in length and where they meet. Now if you project that over, we get true projection on this top guy right here. So we see the distance from the center to here, only on the top one. Due to the projection, you start seeing this guy, and they can look at it and say, well, why is this one's much shorter? It's somewhere else. Or this one doesn't go to the quadrant point, okay? Because it's just not looking right. And you notice the distance of the hole from here to the edge versus here to the edge. Well, is this distance right here from the center of this hole to the edge the exact same as this hole to its edge? It is. It's the same distance. The projection doesn't look like it though, because it's a foreshortened surface. So what we do is when we get these types of things, we say, you know what, this is gonna confuse the heck out of somebody. All they really need to know in this view is the distance from the center to the center of those holes. And so we get rid of all these arms, we take this one, we're gonna rotate it down to the bottom. Okay? So they take this, and we do it in our minds, we're just gonna take this guy down, and we're gonna put it right here. And then we are gonna project only this one and this one. And we project just those two. Much easier to read. The sides are true size and shape versus foreshortened. No mistakes are going to be made. Keep in mind, they'll still have this view. They know there's 5 of them out here, even though you're only showing 2 here. They know that. They've got this. Okay? This is the revolved convention.
Why do you have to put 2? Why isn't 1?
Well, you know, this is an object I would maybe even think about doing a revolved or a partial to get rid of all this misleading, because this is all the misleading stuff. Now, I do need this information right here. Okay? So if I was doing a partial, I would be breaking this somewhere down in here so that they can see the thickness of this negative cylinder. Okay?
So there's no confusion, they wouldn't think that that has to be straight, you know, and then you have to monkey around with 5.
No, they've still got this
You know
view.
that, I mean, they know it's involved.
Yep, they know it's revolved. I think the next figure really brings that out. Look at 1086. How would you like to decipher
Oh, yeah.
this view right here?